Okay, let's dive into this. You know, we rarely stop to think about the invisible engine powering literally all of our seamless tech experiences. From the phone in your pocket to the massive servers running modern AI, there is a hidden heartbeat making the whole shebang possible. So today, in this explainer, we're going to explore the fascinating evolution and the underlying architecture of random access memory.
Here's our roadmap for the journey today. We're going to start with the processor's bottleneck, look at how early engineers solved the chaos, map out the massive DDR revolution, explore the specialized memory era, and finally finish up with what I call the never-ending race.
All right, part one, the processor's bottleneck. Let's talk about the speed problem. To really grasp why RAM had to be invented in the first place, imagine you're building the world's very first computer. You've designed a processor that is incredibly fast, but there's a fatal flaw. Every single time it needs data, it has to fetch it from a desperately slow hard drive. It's exactly like having the world's fastest, most efficient chef working in a kitchen, but every single ingredient they need is locked inside a warehouse 10 kilometers away. The chef isn't slow, right? The delivery is. To fix this massive bottleneck, engineers invented RAM to act as an incredibly fast memory space sitting right next to the processor, holding whatever program you're actively running.
The first really practical attempt at this was SRAM, or static RAM, and it was pretty ingenious for its time. It used these tiny electronic circuits called, believe it or not, flip-flops. They acted just like miniature light switches. Once you turn the switch on, it stays on, meaning the processor could access the data almost instantly. But there was a huge catch here. Every single bit of data required 6 whole transistors to work. If you wanted to cram just 1 gigabyte of SRAM into a modern computer, you'd need 6 billion transistors. That chip would be massive, insanely expensive, and it would generate way too much heat for a standard PC.
So, enter Robert H. Dennard. In 1968, this brilliant engineer proposed a radically simpler design called DRAM, or dynamic RAM. Instead of relying on 6 transistors, Dennard's absolute genius idea was to store a bit of data using just 1 transistor and 1 microscopic capacitor. Now, what's really interesting about this is how that breakthrough made memory chips dramatically smaller and cheaper, which finally allowed computers to have megabytes of RAM instead of just kilobytes.
But, physics always introduces a new problem, right? Think of a capacitor like a tiny bucket holding a small electrical charge. If the bucket has water in it, that's a 1. If it's empty, well, that's a 0. The issue was that these microscopic buckets leaked constantly. So to stop the computer from instantly forgetting whatever you were working on, the system had to dynamically refill every single bucket thousands of times every single second. And that constant refreshing, that's exactly why we call it dynamic RAM.
Moving on to part 2. Solving the chaos. It's time to sync up the CPU and the RAM. So, fast forward to the 1980s and 90s, and the computing world is facing a totally new crisis. Processors were getting ridiculously fast, but RAM was acting completely independently. I mean, what happens when a teacher asks a question and the students just shout their answers at random times? That was the pure chaos of early computers. The CPU would ask for data and then just stand around twiddling its thumbs because the RAM would answer whenever it felt like it. The brilliantly simple solution to this was SDRAM, or synchronous DRAM. Engineers basically forced the processor and the memory to move together on the exact same clock rhythm. Because everything finally became predictable, the CPU didn't have to wait around anymore. It permanently solved that shouting classroom problem, and overall system performance absolutely skyrocketed. Which brings us to part 3, the DDR revolution, where we start doubling the speed. Because even with the processor and memory synchronized, computers were still totally starving for more bandwidth. So how do you double traffic without building a wider road? Imagine a highway where cars are only allowed to move when the traffic light turns green. Well, engineers figured out a way to let data cars move when the light turns green and when it turns red. This instantly doubled the amount of data traffic without having to build a wider physical pathway. This massive breakthrough was, of course, double data rate memory, or DDR.
And this rapid drumbeat of progress really changed everything. In the year 2000, DDR1 dropped, giving computers the massive bandwidth needed to run early Windows apps, basic pixel games, and those classic MP3 players. But by 2003, simply cranking up the clock speed made everything run way too hot, so DDR2 arrived. Then in 2007, the multi-core revolution hit, requiring DDR3. And in the 2010s, the crazy data explosion of 4K video and massive open-world games demanded DDR4.
Also, keep in mind, because of the massive physical and architectural changes between each of these generations, upgrading to a new RAM standard means you actually have to upgrade your entire motherboard too.
Now, these generational leaps were achieved through two simultaneous trends. As processors got faster, engineers systematically redesigned the internal architecture, like pulling 4 bits of data at a time in DDR2, 8 bits in DDR3, and introducing bank groups in DDR4. But simultaneously, they systematically dropped the voltage from 2.5 volts in DDR1 all the way down to just 1.2 volts in DDR4. This brilliant engineering basically meant your PC could run significantly faster while staying much cooler and a lot more efficient.
Let's see how this builds into the modern era with DDR5. Today, we're squarely in the era of artificial intelligence. Modern processors have dozens of cores moving absolutely enormous amounts of data, so DDR5 isn't just slightly faster, it fundamentally changes how memory works to handle this insane load. Step 1 was splitting the memory into 2 independent 32-bit subchannels, which allows the CPU to grab different pieces of data simultaneously. Step 2 involved moving the power management chip directly onto the RAM stick itself to reduce electrical noise. And Step 3 added on-die error correction to make sure your data stays highly reliable even under immense pressure.
All right, Part 4, the specialized memory era. Let's look beyond the desktop.
So the crucial point here is that everything we just discussed applies to standard desktop or server memory. But not all of your devices use that standard form factor. If you're using a smartphone or a remarkably thin laptop, you're relying on LPDDR or low power DDR. It aggressively cuts down power usage so your battery actually lasts all day. If you're a gamer, your graphics card has to calculate thousands of pixels all at once, so it uses GDDR, graphics DDR, delivering massive bandwidth for smooth gameplay. And if you're running heavy AI models or crazy scientific simulations, you use HBM, or high bandwidth memory. This literally stacks memory chips vertically on top of each other to create an extremely wide path for data, all while staying power efficient.
And finally, Part 5, the never-ending race, the future of RAM. We've gone from massive, incredibly hot 6-transistor chips all the way to ultra-efficient, vertically stacked memory. We have solved bottleneck after bottleneck. But this technological evolution is still unfolding in real time. The story of RAM is far from finished. The future is already knocking on the door right now, with next-generation standards like DDR6 and new compact form factors like CAM2 actively in development in labs as we speak.
Because ultimately, the race between fast processors and fast memory never actually ends. Every single time memory catches up, the processor takes another leap forward. We are basically in a state of permanent technological acceleration. As artificial intelligence continues to push processors to unimaginable extremes, it really makes you wonder, what wild new architecture will memory have to take on next? Thank you for joining me on this explainer, and keep staying curious.